In this lecture, we will solve some examples showing the application of Gauss law. Now, we should know where to use Gauss law. We see that in the expression for Gauss law, what is happening? We are trying to evaluate this integral E dot ds over a surface S. Now, it will be beneficial if somehow this integral is either converted to simple integral. This dot product is having cos 0. Okay, that is cos 0 is equal to 1 somehow. Or one of the component of the field is constant and that can be, let us say, taken out of this integral. So the benefit of Gauss law will be seen only if there are some symmetry conditions which allow to have this integral as simple as some EDS or EDS, and this integral is still solvable in some form, easily solvable in some form. So only then the Gauss law should be used. Otherwise, if there is no symmetry, we should clearly use some other method like directly finding the field using vector integrals or Coulomb's law, or by finding the potential, which we will see later, and from that we can find the electric field. So Gauss law is only useful only if there is some kind of symmetry in the system or in the question at that point. So let us now first solve a simple example of a case when there is this spherical shell, that is a sphere which is empty. Let us say this is spherical shell which is having a uniform charge, surface charge on this surface. Let us say total charge is q, so surface charge density will be q by 4 pi, and let us say this cavity is having this shell is having a radius of r, 4 pi r square. This will be the surface charge density of this shell. Now I want to find the electric field inside this shell. So since symmetry for any point inside, we see that there is no unique direction. This point can neither favor this direction nor this direction nor this direction nor any this direction nor this direction. For this, all directions are similar. So you see, from symmetry we can think that the field inside this shell should be radial in direction. Okay, so from Gauss law, what we will find? We will find that this EDS is simply this thing, and we are also assuming that this, due to symmetry, it is in just radial direction and uniform. So this total, since there is no charge enclosed inside this, the charge all resides on the surface, this is equal to 0. So we find that this ds cannot be 0, so this E should be 0 inside everywhere. So this is the application of Gauss law in finding the electric field uh, inside a spherical shell with uniform surface charge density on it. However, we can find or solve this question in some other way. Let us see the other way. So this is the shell, and let us say we do not know that there is some spherical symmetry inside it or not. So that's why what we are having, we are now trying to uh, derive this same result without using any symmetry condition. Okay, so this is the shell with radius r. So let us say this is some point P. So at this point P, let us say these are two surface area which are making this cone. So this is, let us say, surface area ds2, and this is surface area ds1, and this is r1, this is r2, and from this center this angle is alpha and this angle is beta, but these two both will be radius r only. Okay, so the field at point P will be the density over ds1 4 pi r1 square, and since this is vanishingly small, when vanishingly small, the field will be created in this direction by this ds1 charge, and by the charge on this ds2 field will be created in this direction. Okay, so the total field will be minus sigma ds2 4 pi r2 square over sigma by 4 pi epsilon. I forgot to write 4 pi epsilon is common, so ds by r1 square minus ds2 by r2 square. Now the solid angle, you see that at this point P both are making the same solid angle. This cone is having same size. Similarly this cone, so these two cones are making the same solid angle at this point. So these two solid angles are equal at point P. Okay, so simply what we have to find is that this solid angle is ds1 cos alpha by r1 square and ds2 cos alpha by r2 square. So you see that in that sense we can write it as sigma by 4 by epsilon naught d omega by cos alpha minus d omega by cos alpha, which is equal to 0. This gets cancelled out. So you see, in this sense also we have derived that this field is 0 inside this shell if this shell is having a uniform surface charge density on it. Okay, now in the next application of Gauss law we will see the Earnshaw theorem. So what does the Earnshaw theorem says? It says that there cannot be no stable equilibrium point in electrostatic field except on top of an opposite charge. So this is a very simple theorem and we can easily prove it. How? So what is the meaning of a stable equilibrium point? A stable equilibrium point means that the force is 0 at that point, and if there is small movement then a force will appear which will be trying to again pull that point again to this stable equilibrium point. Okay, so what does it mean? Let us say this is a field created by some electrostatic charges. Let us say these are the charges, some electrostatic charges are there. Let us say these create a field E. Now let us say there is a point charge Q at point P. So let us say it is in equilibrium, that is the total force on this charge is 0. However, now let us move it here in this direction. So if it is a stable equilibrium, so what should happen? A force should appear which should again pull it to back to this direction. Similarly, if I push it here, the force should be there somewhere it should appear, the restoring force should appear, which should again take it to this point. Similarly, if I move it here, the restoring force should be like this. Similarly, if I move it here, the restoring force should be like this. So it means that around this point P, the direction of field should be inward towards this point, radially inwards towards this point. However, as we have seen from Gauss law, it implies that the flux of the field surrounding this surface to this point P will be negative. It implies this will be a stable point if and only if there is a negative charge here. Otherwise, if it is free space and there is no charge, then it will be equal to 0, and this scenario cannot be possible. So in a sense, we have proved that in an electrostatic field there cannot be a stable equilibrium point except on top of a opposite charge. So this is the theorem. Now, although we have proved this is just for a point charge, we can prove it for a combination of charges also, like let us say this charge Q1 and this charge Q2 are connected by a rigid rod. Now we can again find the total force E1 at Q1 plus E2 at Q2. So this is the total force. So now taking the divergence, del dot E1 Q1 plus del dot E2 Q2. Okay, so this will be 0 if it is free space, that is no charge inside or outside, positive negative charge inside this surface. So this will be 0. So F will be 0. So at most, at minimum, this value can be 0 only, not negative. However, for a stable equilibrium, what we need this to be negative, not 0. So this shows that there cannot be a stable equilibrium point in electrostatic field. So this is the Earnshaw's theorem, which we have just proved here. Now, what about if there are so many conductors instead of charges, and that conductors are, of course, let us say charged? So similar scenario will be there. However, this thing will be a little difficult to prove because it will require to prove us that the charges on a conductor take positions such that the potential energy is minimized. So if there are so many conductors, charge conductors, so stable equilibrium point means that if we perturb it, it should come back. Means there should not be any other position with more minimum energy. So it will be difficult here to prove this thing. However, again, on the similar lines which we have seen in this normal point charge cases, we can go ahead and prove that the similar theorem exists for the charge conductors. That is, in electrostatics, for charged conductors, there is no stable equilibrium point. Okay, now let us see something about for in next slide we will see for the stability of atoms. So you might remember that there were so many models of atom which were proposed earlier. Earliest one was, I think, Thomson's model of atom. What it was that that positive charge is spread, and in it electrons or negative charges are embedded. However, later on, Rutherford found that it is something different. Means this positive charge is rather more accumulated as compared to the negative charges. So Bohr's model was there. In that, it was told that nucleus is having positive charge and electrons were orbiting across around this nucleus. But again, we will find in our later chapters that since this is circular motion, and in circular motion there is an acceleration, and a charge, if it is accelerating, it creates a radiation, and if it creates radiation it loses energy, and if it loses energy it should slow down. So this model is not a stable model. So Bohr's model is also not the correct model, as we can see clearly. But the quantum mechanics comes into picture, and what it says that this positive charge, although concentrated near nucleus, the electrons are placed uh, scattered around this positive charge. And why they are just not getting attracted by the nucleus is because of the uncertainty principle, which says that if it, let us say, goes very close to the nucleus, so if it goes very close to the nucleus, then we know that this is very small. So this gets very high, means momentum gets very high, means the energy gets very high, velocity gets very high. So this charge is able to overcome the attraction. So in this way, the quantum mechanics kind of explains the stability of the atom using uncertainty principle. Now let us come to some more important expressions or derivations using the application of Gauss law. Let us derive for a very long line charge. So let us say this is a line charge which is having lambda coulombs per meter line charge density. We want to find the electric field due to this line charge. So by symmetry, we can see that for this line charge, the field can be in this direction, this direction, this direction, this direction. Okay, but it cannot be in this vertical or downward direction. Why? Because for any other point there will be field which will be cancelling it. So we see along this line there cannot be a field. Field can only be in this radial directions only. So by symmetry, what we will do, we will draw a cylinder about this line charge. Let us say this cylinder is having length delta L and this radius is R. So the total flux inside this cylinder will be this surface, top surface 1, bottom surface 2, and this curved surface 3. So the top and bottom surface will have normal along this line charge, or in either in the top direction or the bottom direction, but field is just radial. So you see for these bottom and top surfaces, this top and bottom surface, E dot ds will be equal to E ds cos 90, because E is like ds is like this and E will be in the radial direction. Okay, so this angle will be 90 degree. So this angle is 90 degree. So this cos theta will give to 0. So only survivable part in this integral will be this. So for a given distance from this line charge. From symmetry we expect that this E will having same magnitude at the same distance from the line charge. So this E will come outside and ds, and E dot ds is already converted to E ds cos 0 because both are in same direction, ds as well as E. So this is lambda by epsilon naught into delta L. So this is the charge enclosed by this cylinder, lambda into delta L and divided by epsilon naught. So E into 2 pi r into delta L, this is the area of this curved surface, is equal to lambda into delta L by epsilon naught, or it implies E is equal to lambda by 2 pi epsilon naught r. So this is the magnitude of the field, and we already know that the direction of the field is in the radial direction in terms of cylindrical coordinates. So in this way we have found the electric field due to an infinitely long line charge. Why infinitely long? Because we have considered that there is no end effect, that is field is always radial instead of any other component of the field. Now let us see another case of infinite sheet of charge. Let us say there is this sheet with having surface charge and sigma s. So we want to find out this field due to this surface charge density. Now we are again assuming that this is infinitely large in all the dimensions, so that end effects are not there. So what we will do, we will make a pillbox I wanted to show dashed, means both directions. Okay, so by symmetry we are going to find that the field is going to be in this direction on the right hand side and in this direction on the left hand side, and field will not have any component in this direction. So we see that this curved surface area is not going to have any component in the flux calculation of the integral. Only these two surface area, the top and the bottom, these are going to contribute in the integral. So, and this is the charge which will be enclosed by this cylinder. So this cylinder is going to enclose, let us say this is having radius r. So, or let us say this is delta s only. So this will be delta s in magnitude, and this also will be delta s. So sigma s into delta s will be the charge enclosed, and the first surface area delta s plus the second surface area, okay, will be there. So twice of E delta s is equal to sigma s delta s by epsilon naught. This will get cancelled out. So E is equal to sigma s by 2 epsilon naught, and direction is the normal direction from this sheet. So you see that this field is not depending upon the distance from the sheet. Why? Because we have assumed that this sheet is infinitely long from in all directions. So no matter how far we are from this sheet, the charges which are going to impact or create field are going to increase in the same proportion as the distance, like in x direction as well as y direction. So kind of a squared relation is there. Similarly in this side also, so squared relation is there, and the field reduces by 1 by r squared, charge will increase by again 1 by r into r squared, so this will get cancelled out. So in this sense we can see that E is going to remain constant in magnitude on the both sides of the sheet. Okay, on the left hand side direction of the field will be like this, on the right hand side direction of the field will be perpendicular to the sheet. So in both cases the field will be perpendicular to the sheets. So this is the application of Gauss law. Now let us see what happens if there are conductors. That we will see in our next lecture. So if you find that this lecture is helpful to you, then please share and subscribe my YouTube channel. And we also created a doubt discussion group in Telegram, whose link is given in the description of this video. Please join it. Thank you.